going to try to get a contradiction. Okay? So, and I'm going to use the nested interval theorem to help here. And the idea is, well, let's see. The idea is, if this is true, that this cover has no finite subcover for AB, would you agree that it's also true for any subset of this, sub-interval of this set? Would you agree it's also true? That is, if I divided this interval in half, call this point C, maybe C1, would you agree that this cover covers both halves? Yes? Why would it have to be the case that at least one of these halves also has no finite subcover of this red cover? Yes?
Because if both halves had a finite subcover, then we take the union of those finite subcovers and have finite subcover.
Excellent. Everybody happy with that statement? That is, if both halves had a finite subcover for this cover, you just union those two collections and you'd have a subcover of the whole interval. Would you agree? Yes? So, oh, great, I have an interval. What's the next? What do you think I'm going to do next? And while you're thinking about that, let's write down what we've just said. So then, G alpha covers both AC1 and C1b. Everybody agree with that? And the claim is that at least one of which, at least one, maybe both, but at least one has no finite subcover. I'm just going to start abbreviating finite subcover if you don't mind. I'm just going to write FS now because I might have to say that again. Okay, at least one has no finite subcover. Which one? Well, I don't care, but say one of them. Let's say it's I1. Let's call it I1. Interval 1. All right. What do you think I'm going to do next? Suppose it's this one. Bonnie? Ooh, split it again. Let's split it exactly in half. Let's call it the next one C2, the next halfway point. Okay? I didn't say that here, but what I'm saying is choose the CI so they always split halfway. Okay, call it I1. Great. Without loss of generality, suppose it's AC1. That's the I1 is. So without loss of generality, this is shorthand. If you're writing it out, you'd write without loss of generality. Let's say I1 is the first interval, just to be explicit, AC1. Let's say that has no finite subcover. Okay, well then let's subdivide again. I'm going to say halfway using C2, which is the halfway point. And once again, we'll note that, now what are the two halves, Bonnie? AC2 or C2, C1. Note that this or this, one of them, has at least, so note at least, okay, one of this has no finite subcover. Excellent. Now what? Subdivide again. Thank you. Lindsay's saying subdivide again. So I'm just going to say here continue. And we'll obtain a sequence. I1 contains I2, contains I3, etc. Yes? Of nested closed intervals. And what else is true about this nested set of closed intervals? They're doing what? Oh, they all what? Oh, okay. Well, we're about to, yeah, we're going to use that in just a sec. But what can I say about these intervals besides the fact that they're nested and closed? None of them has a finite subcover. Agreed? For that original red cover. Not only does that, none of them have a finite subcover, but the other thing is I've chosen them so they're always getting smaller and smaller, right? They're always decreasing by half each time. So I'm going to make those two observations. Each halved at each step, and with no finite subcover of the G alphas. Okay, so since I'm gonna refer to this, I'm gonna call this property Cyclops smiley and this double smiley. Okay, these are important properties we're gonna refer to again. But now I have a sequence of nested closed intervals, and so Maya's thinking, oh, I could use this fact, which we conveniently proved last time. And Jacob is saying, this means that these nested closed intervals, what? Good, so there exists a point in all of them. Great. So by the nested interval theorem, there exists, let's call this point, I don't know, why don't we call it x? There exists x in an in for all n. There's a point in all the sets. All right, so let's just draw a picture here. This was our first interval. This was our second interval. Maybe this is our third. Maybe this is our fourth. Maybe this is our fifth. Each time you're picking one of the two halves at every step. Would you agree that this, because of this theorem, would you agree that there is a point in all the sets? Maybe this point x lies somewhere here, yes? Do we have a contradiction yet? Not yet. So what? I have a point that's in all the sets. So what? Emil? Look, yes, this point is, this single point is somewhere on this interval. Would you agree it's in some open set of the cover? Maybe it's in this one. Let's make this one special. This one is going to be kind of a brighter red here. This point is in one of these open sets. Yes? Okay. So then what? Think ahead as to where's our contradiction coming. X is in some. Let's call this the special element G alpha. Let's say some G alpha hat of the cover. Okay, so what? X is in one of these open sets. Why is that going to contradict anything about our nested intervals? Jenny? Oh, yes. X is in an open set. So X is an interior point of this set, yes? Therefore, there is, in fact, an interval around X that's still within this element, G sub alpha hat, right? Okay, but why does that say anything? So let's say, so I'm going to mention that this is open. So there exists an R bigger than 0 such that a neighborhood of R around X is completely contained in what? G alpha hat. Help. I agree. There is a neighborhood around this point. You don't mind, I'll make this a green set. This green set